Florian Levet. His research focuses on developing new open source tools for single molecule localization microscopy. So thank you. We are looking forward to the presentation.
Thank you, Anna, for the nice introduction. So as you will see, today I will present something that is not really my work, that I contributed to, because that's kind of a funny story. At some point, I got an email from Krista telling me that I was doing nothing during the workshop. So maybe I misread it, but I felt like I needed to do something, like having a talk. And then I went to the program and the session, and I was not really knowing what I could do during the workshop. So I was really considering playing possum, like trying to avoid the bullets. And then I think, okay, no, I contributed to something that could go to this error and performance session. And this is really the work of Daniel Neves, that is a postdoc in the lab of Dylan Owen. And I have a big shout out to give to Daniel, because he gave me his slide. So most of the slide that you will see is slides that I put in my layout. But yes, a lot of his work, and it's very nice from him to give it to me. And just a small thing is that I'm not a group leader. I'm a PI in the team of Jean-Baptiste Ibarita at the ANS, but this is a French system. So I'm still having people and all this kind of stuff. So this is something that you already seen in the slide of Sean. So we'll not go very long on that. Single molecule localization microscopy. We managed to make them blink, localize them, and then we have a better resolution. So in the end, from this bulk fluorescence image, we managed to have something that is more resolved. And here it's fibroblast for adhesion site. And the collaborators were interested in trying to see how the molecule were organized in the adhesion site. But then now we don't have image, we have point clouds. And still, this is very important to have the access to this information, because heterogeneous distribution and association of biomolecule is essential for many biological processes. And really, this spatial distribution of the protein will affect their ability to interact with other molecules and certainly directly affect their function. And so clustering of these molecules can be related to a lot of different things like trapping, localized enrichment. And now single molecule localization microscopy is really a well-established tool for biologists interested in this protein organization. But then the question is, how can we use the pointillistic nature of single molecule localization microscopy to do some quantification? Because when the technique was out, the first thing was to reconstruct super resolution images, but still you have this localization, and there are certainly more information than trying to go back to images. And the first thing that came very rapidly is what we call global clustering. For instance, the replay function. So this is a way to analyze point cloud where you will define some radius, and you will grow iteratively this radius, compute the density, basically the number of localization that you have inside this radius. And the thing is that you know the number that you would expect from a complete random distribution. So when you do the plotting of your curve in the end, if you have something that is completely random, so no clustering, you will have a curve that is around 0 like that. And if you have some curve that has this shape, you have the maximum radius of aggregation in your data. So it gives you an information about how your protein aggregated, which is already something. I mean, because this is statistical measurement. So you will be able, for instance, to compare some condition, like this one is more clustered, this one is less clustered, but you don't have access really to the clusters. So there is more to learn from single molecule localization data, because they are really rich in spatial information. And so a lot of people developed complete clustering, which is really algorithms that segment the cluster in order to have access to the quantitative information of these clusters, like the size, shape, number, and density. And this is where my reason why I was part of this work is that because I developed methods in order to do single molecule localization microscopy data analysis for more than a decade now. More specifically, I use Voronoi diagram in order to analyze single molecule localization microscopy data. So Voronoi diagram is the dual of the Delaunay triangulation. Here you can see a Delaunay triangulation of this point cloud, where basically you have a mesh that is created with some properties, where like you know that the triangles won't overlap. And when you have the Delaunay triangulation, you can compute the Voronoi diagram. And why it is interesting is that because when you have the mesh here, one triangle will connect 3 localization. So it can be difficult to see how you can use this triangle in order to add some quantitative features to your localization. On the other hand, the Voronoi diagram, which is a space subdividing technique like the Delaunay triangulation, will create one polygon around each of your localization. And basically, any point inside the polygon is closer to this localization than to any other localization. And you can see that, for instance, this edge here is a bisectrix of this triangle edge. So this is not how exactly you compute the Voronoi diagram, but that's the basic idea. And now you have objective representation. So for one localization, you have one polygon, and it's also true in 3D. Here I show in 2D because obviously it's easier to see. And the Voronoi diagram has some really nice features, like the connectivity, is that by construction, you know that this localization here is neighbor to this localization here because they share one edge on the polygon. And you have the scalability, where the denser the localization will be, the smaller the polygon will be, which would not be the case if you used an image, obviously. And so what we did is that we used that in order to generalize the computation of local density in the Voronoi diagram. And we show that we were able to do a very simple kind of normalization. It's not a mathematical normalization, but it's working very well, where if you have something that is of similar spatial distribution, it's the same cluster, but just with different density, you are able to normalize this density just by dividing with the average density in your data. And this is very important because when you are using single molecule localization microscopy, we'll have very different localization density depending, because there is a lot of experimental parameters. There is the fluorophore, the blinking kinetics of the fluorophore. There is a time of acquisition. There is a method. You will have more localization with DNA panes than with Palm, for instance. So being able to really analyze this with respect to the density is important, and that's what we did. And we released a first software in order to do that in 2015. Then we spent a few years in order to do colocalization analysis, again with Voronoi diagram. So we just kind of adapted the Pearson coefficient and the Menders coefficient to single molecule localization microscopy. And we use the Voronoi diagram as a proxy for the pixels that you have when you are using this for images. We released a second software for that. And then at some point for me, I was already developing stuff for almost a decade about that. So my software was really hell. It was really difficult to continue to develop with that. So I decided to do a new platform because, well, why not? And in this case, it's really doing 3D, 2D visualization. You can do batch processing. You have DLL. So it's a lot easier for me, for my life now, to add stuff inside this platform. And so with this, we have done a few analyses with some collaborators from the lab, from the Interdisciplinary Institute of Neuroscience, and for collaborators. And then since it's out for almost 10 years now, it had been used by a lot of people. So this is what we did for single molecule localization microscopy, but we are not the only group that use that not use, but develop new technique in order to do the quantification of this data. So for instance, one of the first was already in 29, and they used Delaunay triangulation in order to do segmentation. It was the work of David Badley. The most used technique in the field for segmentation is certainly DBSCAN, where you have two parameters, a neighbor search and some other parameters that you use in order to do the classification of the density, because basically your neighbor search is used in order to compute the density, and then you use some criterion in order to do the classification, and then you end up with some object. You had Tomato that was developed by in UK, where it's a topological method, where you have a neighbor search again to have some density, and then you are using a persistent threshold in order to create first cluster and then merge them together with something that is more persistent. And or you have CAML, cluster analysis with machine learning, which was developed in the team of Dylan Wen. So again, same team than this work I will present, that is using k-nearest neighbor distances. So you have the localization, you will create images of the KNN distance, and then you use a convolutional neural network in order to do the clustering. So really now it's complete clustering is the dominant form of analysis for single molecule localization microscopy, because you have really access of the distribution of the cluster. And so I already shown a few of them, but there is a lot more techniques that are developed. almost dozens per year of new methods in order to do this kind of analysis. However, there was no consensus on how we should assess this clustering algorithm. And that was the idea of Daniel and Dylan, to really develop a framework in order to assess how clustering methods would work and would accurate the result will be. And so the idea was to use two different features, but point membership and feature detection. So point membership is say which points are clustered, and feature detection is what features are detected and how can we use them in order to have some measure of the quality of the segmentation. And so for the first one, the point membership, the first one with the RAND index. So the RAND index measures the similarity between two complete clusterings. So all points must be assigned to a partition group. In order to, all points in the end will be used in order to compute the RAND index. And so the value that you got in the end is between 0 and 1. So no agreement to perfect agreement. If you have the small equation, it's really this thing. So the number of agreements divided by the number of agreement and the number of disagreement. And I have a small example in order to show. So you have two clusterings that you want to compare with the RAND index. What you are going to do is every one of these link between the different cluster in your clustering. And then you try to say, okay, for instance, here, these two are in the same cluster. They are in the same cluster also in this proposal. This is A, this is agreement. Same here. Here you have the agreement in the disagreement in the end. So this one is not in the same cluster, not in the same cluster. So this is also agreement on not being in the same cluster. And you do that for every one of these relation, and you end up with your computation. And if you do that on this kind of data set simulation, so you have the grand truth, some result, and a second result. So obviously the second result is very high, but in the end we can see that this one is quite high, 0.5, while really the clustering is garbage. So RAND index is really not good when there is clustering by chance. And so we went to use the adjust RAND index, which is a modified version, which accounts for this situation where you have chance clustering. So here you can see it's index divided by max index minus the expected index, but yeah, well, expected index, what it is, not very clear, but I will just show you that after. And what is important now that the array will be between -1 to 1, and gives you a more idea of what happened in your data. So what you are going to do is basically compute a contingency table. That would be here, this is your first clustering with all the different clusters, the second clustering with all different clusters, and you will just do some computation of how many of this cluster is in this cluster. So I have an example just after in order to show, and then you have this equation with this being binomial coefficient. But again, example just after, it will be easier. So again, same example. If you go to the result one, in the end you have, so grand truth, your results, grand truth, your results. You have three clusters. Well, background plus two clusters, but three classes, let's say. So you have three classes here and here. And if you go to this part, for instance, for the one, we'll see you will compute the 1-to-1. So 1, 2, 3. This is this 3. And you do that for all these different combinations. And then you can compute the different sum that you have here. And you end up with this value here. So now you are really close to 0, meaning that you don't have a good correspondence between your two clustering, which is what you would expect. And if you go to the result 2, you have a much better value. And so now in the end, you can see that adjust RAND index gives what you would expect is that result 2 is really good, result 1 is really bad. So this was for the point membership. About the features detection, they use the intersection over union. So something that is quite known now with deep learning. And this is exactly the same idea. So you will create your polygon, your object, and then you will compute the intersection over union. And that means that here the edge of your cluster are important, not really the number of localization inside your cluster. After that, we define several simulations that should mimic the biological single molecule localization data that you get when you are doing an acquisition of a biological sample. So 10 different clustering, different background to cluster ratio, different morphology of the cluster, isotropic, anisotropic, well, kind of few different simulation, 50 simulation per scenario. And then you run your analysis. We tested all these different parameters, all these different methods where you can see that some are automatic, some are with some parameters. And if we go with an example, using DBSCAN with scenario 2, so you can see some of the simulation of the scenario 2. You will apply DBSCAN. So DBSCAN has two parameters, mean number of points and epsilon. Epsilon is the radius of search. Mean number of points is the value in order to do the classification between point in the cluster and background. So you have a range for the two parameters, and you will apply the analysis. Well, you apply DBSCAN, you have the result, you compare to your ground truth because it's simulation, and then you can do this kind of map of your value. This is for one data of the scenario. You do that for the 50 if you have 50. And you end up with the mean ARI, mean IOU, and the variance. And because you have these two, you can very easily find the best parameters for this scenario and apply it and see and really find these optimal parameters. So we did that for all the simulation. So we have 10 scenarios, but we also do the same 10 scenarios, but with blinking. So first one is like you would have a perfect world, no blinking. It's really nice. Not really what happened in real life. So we have also the scenario with blinking. And what we find is that generally algorithms that have more parameters perform better, and would can be of expected because you have more room to really fine-tune your parameters. It's true on simulation. Then on real data, it's always a little more complicated. We also saw that heterogeneous cluster pose a problem, but again, that would be expected because these data are not really good to separate things that are very close. So they will segment one cluster when there is two if they are close. So this is something also expected. But what they show, what we show in the paper, is that this is, again, when you go to biology, difficult. Okay, we have done that in simulation, which is fine. You can say on this simulation, this technique is performing better, but what about biological real model? And the idea here was to try to use this simulation in order to find parameters for your data. And the basic idea is that you have your single molecule data. You will split your data in area of 2 micrometers square. Screen that on K-replay in order to know if already your data are clustered or not. So if you have something where there is no cluster, we'll have, again, this thing. So you don't go further in the workflow. And if you have that, you know that there is some cluster, so you will go further in the workflow. So either you try to correct for the blinking or not, and then they develop a method to find similarity between two data. So the idea is that you have your data, you will try to find the similarity with the simulations that were already defined in order to find which simulation is better, well, is very close to your biological data. And then you can go to the result that we got from all the scanning of the parameter of this method in order to find the best performing method. So they had some FGFR1 data, so don't ask me what it is. No idea. You have the different scenario. They apply their method, which is, you can read it here, and they find that the smallest mean dissimilarity is the scenario 7, where you want to have, because this is the dissimilarity, you want to have the smallest value. And that in this case, DBSCAN was the best scenario. And so they apply DBSCAN with the parameter found from the simulation in order to do the analysis of the FGFR1 clusters. So in the end, cluster analysis is highly suited towards single molecule localization data, very popular approach. And this framework here is really here in order to help for assessment of new tool. But again, you can try to use that in order to at least a first view of what you could use as parameter in your biological data if you have something that is similar to the simulation. Obviously, if it's not the case, well, you're back to the drawing board and trying some parameters. And in this case, maybe DBSCAN is not the perfect one because to a parameter, when you don't really know what you're doing, it's complicated. But still, it can be applied to 2D and obviously 3D. even if when you do IOA on 3D on some polygon, it's not that easy. It's harder than with images, but still you can do that. And then, as I said, it can help with your analysis of single molecule data. And I'm done. I want to thank the team. And so my team leader, which is Jean-Baptiste Ibarita, collaborators, and obviously, which is not clearly not INS here. I forgot completely to change that, so it's not INS, but Daniel and Dylan for really having done this much of the work that I just presented. Thank you.